just fires. Just eat the robot on the other side.
Guys, you're all looking at this program after this meeting. Give your presentation. The way it's going to be set up is you're going to give your presentations, talk to the TAs in the morning. You're going to give your presentations. And after you finish your presentation, you're going to get the TAs for the validation. And so, we'll just have that going. We do need you guys to stick around. The entire time presentations are done. So when you finish your validation, I need you guys to go back and sit as a audience for your peers. So you can see our presentations. The rest of the schedule here, guys. So as we mentioned, we're a little bit in. So we're going to do the introduction to robotics. TAs also know that we might have some groups that are getting started with the robotics stuff this week. And so guys going looking for robotics parts or support to getting started project, and TAs are prepared for that. So I want to point out the primary times. We'll be doing qualified. We'll explain this process in a few minutes. For qualifying happens during the lab period of week 13, week 14, and week 15. And so, that being said, if you want to qualify to catch a TA in the lab period, it's log report time at any point. Okay, so we want you guys to, if you're wanting to get started early, stuff kind of prepared, we have other stuff going on. You can go ahead and get started this week. Also, you guys know to be preparing a memo as well for the project too. So you have that date as well as you can think about it. But all we really have left are the two projects in test 3. All right, so test 3 is happening on the 17th. Okay, that's all going to search sheet so I want to go through the documents for the project. If you go to campus, I've already published the robotics project, and so let's talk about what you want to go through. Here are the instructions. I'm going to go over that first. In addition, you have a parts list for your consideration for the project is cost. It's going to be tracked by what parts you use. You got also, just like your project one, guys, you have a shell program. It's important for you to realize because you don't write the robotics from scratch. We had a group last semester that didn't understand that the shell program exists. Okay, so just want to emphasize, make sure you download the shell program just like you did for your project one. And then there's a bunch of resources here to help you guys out. So today we're going to kind of skip the servo control for today. We'll get to that on Monday. But here's a resource for the servo control. You guys can use that as a resource. In addition, we're using a bit of hardware. We'll actually bring into my Rio on Monday. We'll talk a little bit more detail about my Rio. So, but the short is, the my Rio is the robotics version of the MechLab. So it's for student robotics projects. So the my Rio comes with accelerometers, it comes with Wi-Fi, it comes with USB sensor ports, it comes with more connectors for I/O, and it comes with a processor that is way bigger than MechLab. That's good for robotics projects. So we'll save that for Monday. We'll talk more in detail about the my Rio. So the Rio, to give you guys the idea and perspective, so a lot of you guys have used Arduino before, and Arduino is great. Right, so you would use Arduino, in fact, in a lot of applications because the my Rio costs you probably about $250, which is a low price point for the hardware that you actually get. And so you would use the Arduino if that suited your needs, right? It's lower cost. You could probably online, like Alibaba, you can get Arduinos for like very cheap right now. You just look at Alibaba, AliExpress, and you can get something for less than $10. All right, so it's open source, it's very effective platform. But anytime you're doing, so let's say that you're developing a quad rotor or something like that, if you need a much better processor, you can faster response time, you need power, you can benefit from some accelerometers, USB, all these different things, or I/O. It's smarter, instead of trying to build up an Arduino to handle all that stuff, the bottom line is the processor on an Arduino, the primary chip, will not be able to do the things that you could do with a my Rio. My Rio's central chip is a dual core FPGA and one chip. And so there, we'll talk about some of those benefits next time, all right, but it really is ideal. And you can program it using MechLab2. You can also program it with C++, or you can do both. So it's a really, I think, effective platform for student projects. We'll talk more detail about it next time. We have, for those of you guys that haven't, that we're using Tetris Prime as our build system, so it's very similar to like MechLab2 components. So if you've never built something through like a Tetris or Vax or whatever the case may be, here's like getting started with Tetris Prime. It just talks about assembling pieces of art. So y'all have that as a resource. And then I've made a ton of videos that support robotics. All right, so what I ask you guys to do, just like the first project, if you watch all these videos, and they're 1 minute videos for the most part, if you watch them, they will get you started with the shell program, they will get you familiar with the components and how you connect things up. We have a couple of videos on pulse modulation, which is key for servo control. You guys have all these things at your disposal. In addition, if you guys have a question, just like project one, I might answer the question by making a video. And so the reason why we have so many videos is these are answers to questions that students have had in the past. So if you guys have a question or you're having trouble with a particular thing, I might say, all right, that's a great question. Let me make a quick video, and I'll go ahead and post it to the campus site. So I want to open up the first document here. This has the general data acquisition. So if you hear me say robotics project or data acquisition part 6, I'm talking about the same thing. They are the same thing. Robotics competition and data acquisition part 6 are the same. All right. So getting started, once you guys open up this Word document with the instructions, this is a competitive design competition. But we also should mention that the project itself is open just like your first project, okay? And so building the robot, help each other out, do as much as you can to support each other. The memo I need to make sure I specify is individual work. So as part of this, you have to write a memo for your submission. It's not a group memo, it's not a class memo, it's your individual work that you capture in the memo. So just like any other memo we've done, like if you guys capture like a table or you're gonna have to do a cost bill of materials. That bill of materials can be shared because it's a table. It's in your work. You take an image of your robot as an example. I think I asked you guys for that. That's a picture that can be shared. But the text of the memo that you write needs to be your individual writing, your individual work. All right, the design project, the premise here, you work with some robotics company. You're trying to design a robot prototype. All right, and so the criteria for the robot, the first one is the robot should be able to follow a wall autonomously. So my robot, I'm trying to follow this wall. You're guaranteed in what you write that you will not have an obstacle directly in front of you. And you will just have a wall to your side. So there will be no need to have a sensor that's pointing directly forward so you don't ram into something. And you're guaranteed not to have an antenna directly in front of you. All right? The other second criteria here is, let me say another word about following the wall. Right, it's not fair game. So the arena is going to be, we're going to alter the center kiosk with some wooden panels. And when we say alter, the teams are setting that up right now. Go into the lab, you see the competition track. All right, so the track you see in lab will be the track that we use for the competition. So the actual idea of autonomously following a wall, you need to use sensor information to actuate the motor. Okay, that's what we call a state machine, right? State machine. It's not legal for you to have a robot that just drives around. Right? That would not be using sensors. That would not be, yes, that would be a form of autonomy. You have to use a state machine to control robots. Okay. All right. So follow the wall autonomously. Robots should be fast. Okay, what is the competition? The competition is a chase game. All right, so on the track, and think about that center kiosk is rectangular. So like we might add wood panels and change it into like a hexagon shape. All right, we might just slightly alter it. And you'll be able to see the shape when you guys go to lab. But the idea here is chase game. We're going to start 2 robots for the competitive portion at the same time. All right, you're going to follow each other on the track. First robot to catch the other one is going to win. All right, so that's why we have speed and also reliability. I'm not exaggerating when I say that we've had this competition before, where a robot super fast inches away from catching one of the robots, crashes into a wall, and the other one kind of creeps along, comes around the track and catches. So reliability is, I would even argue, especially if all you want to do is get full credit for the assignment, I'd argue that this is way more important. In fact, I would give you the suggestion that you're going to want to get started with something that is slow and reliable. All right, so that you can get your feet wet and get comfortable and get something that works. And then you're going to want to start adding speed, increasing the motor speed after you get something that is reliable. There is a constraint here on the cost, and so I'm going to bring up the Excel spreadsheet that allows you to calculate that in a few seconds. But your robot cannot exceed $375 of cost as said by the spreadsheet. All right, what we will do is, the day of the competitive portion of the competition, what we're going to do is when you disassemble your robot, there's going to be a TA there that's going to be able to verify that your robot is under the cost budget. All right, there's no benefit to being way under the cost budget. Well, there's a small benefit. But there's no primary benefit to being way under the cost budget. Okay, so your limit is $375. All right, you can get as close to that as you want without going over. All right, and we will check the competition. Also, we have to program the robot using the MyRio software and hardware. All right, so there's no other deviation from that. You have to use the MyRio. All right, and then this last one is important. Okay, only one sensor type is accepted. Infrared sensor. We actually have two different flavors of infrared sensors. We have a very few number of long-range IR sensors. So those guys that have to know, make note of the fact that the long-range IR, its max distance detected is about 1.5 meters. Whereas the short-range IR, its max distance detected is, according to the data sheet, 80 centimeters. All right. So you get a lot more kind of distance with the long range. All right. But it's worth mentioning two things. Okay. The long range IR, we only have a few of them. So if you don't get one, it's first come, first served, and you have to get those from the TAs. So that's the first consideration. Next consideration is long range IR has a larger dead zone, has a larger, not dead zone, but you guys follow me, right? So we get too close. We learned about that. Overestimate the distance. Okay, so it has a larger. That's the usual ratio. Yeah, so you know the graph goes up and then down, and you know when you calibrate it, you try. So it's like tolerance. Range. Okay, that's the blind spot. That's the blind spot. So when we're using IR sensors, we try to avoid being in the range of the blind spot. This particular application actually doesn't hurt you too much, the blind spot you set, because if you're close, it overestimates the distance. All right? And so, well, let me think about it. I'm close. I overestimate. And I'm further. Yeah, that could be problematic. So you're going to want to try to avoid being in the blind spot, okay? Because you don't want the robot over to not understand this position. And so how do you usually deal with that? You usually deal with that with how you mount the sensors. So that is the consideration when you guys are making your robot sensor placement is feedback. All right, you can mount the sensor into the body a little bit as we say. You might also, in terms of sensor placement, you might tilt the sensor at a little bit of an angle if that is advantageous. These are factors that are tied to the IR sensor. The other consideration for IR sensor and the comparison between the two is that sure, the long range gives you more distance, but the resolution is not nearly as good, right? The resolution is going to be better for the short range IR. So if you're able to stay in the pocket, right, at a certain range, so that from experience, you guys also know, all right, that it says 80 centimeters, that IR sensor says 80. If you get around 80, it's really safe. Really, the effective range of that short range sensor is probably more on the length of max of about 50 centimeters. Okay. But if you're in the pocket and you're within like 20 to 50 centimeters, the IR sensor in the short range is going to be more effective. Now, I will say that most people do tend to favor the short range for this application. But one thing that long range will give you is it will give you a bit more of a delta. If you're not staying close to the kiosk, you venture away, it will still be able to get you decent readings on the order of 80 centimeters, 90 centimeters away. Whereas the short range will not be able to carry that. This says robots should use infrared sensors. I probably should change that, but I want you guys to make a note that you can do this entire thing with one infrared sensor. Do the whole application with one infrared sensor. Typically, what do students do? So if you look at .NET, this is the track. We're going to have a start line for one robot on one side and a symmetrical start line on the opposite side. So it will be fair. And the arena will have to be symmetrical. And so robot one here might be using a one sensor approach. Where the sensor is, if the robot's traveling this direction, the sensor is detecting wall. Okay, that's our measurement. Right, for the one sensor approach, you're really talking about three states. State one, I'm within a threshold. So I'm in the pocket, as we just said, right? I'm in this kind of sweet spot. I'm not too close to the wall. I'm not too far away from the wall. I'm in a nice little sweet spot. What do I want to do if I'm in a sweet spot? Yeah, I want to haul it in the forward direction as fast as possible. All right. Okay. Two. Say I'm too close to the wall. Sensor will tell me, because the sensor reading will say a small distance, right? If I'm too close to the wall, what is robot going to want to do here away from the wall? Move back. And with one sensor approach, if I'm too far from the wall, I need to turn towards the wall. Okay, so that's a simple state machine. When we say three states, we're just really talking about, okay, you need three to accomplish it. You have to have three. All right? Three states are needed. Okay? There's no real way to accomplish the project without three states. You might add additional states. So we've had students that have like 6, 7 different states. They might have like a really sharp turn state. They might have a slight turn. They might have move fast, I'm really short, I'm straight, I'm not as confident, so don't move as fast. All these things are determinations you're going to make based on your experience. The other popular approach for this activity, let's say that the robot number 2 here has the 2-sensor approach. So this guy has 2 sensors. One gives me a measurement that's here. Another gives me a measurement that's here. I've seen both approaches in competition. I've seen both. With the 2-sensor approach, stage 1 is difference between sensor measurements. Is between the threshold. All right, so if I'm a robot and I'm following the projector here, my sensor measurements are this. If these guys are similar, I'm going to want to be in the fast forward state. So if I subtract front sensor from rear, and it's a small amount, that means I'm in the pocket on my difference. In the pocket on my difference, I need to be in fast forward state. All right, second case is front is less than rear. In that case, I'm going to turn one direction. The third here is rear less than front. In that case, I'm going to turn the other direction. So depending on your preference here, the two-sensor approach can be useful. It can give you a little bit more reliability from our sensors. Okay, you get a little more reliability looking at the difference between two sensors. But the one-sensor approach is perfectly fair game, and in fact, it can be deployed very effectively. Okay, because all you're looking at is what distance and all the fall. And even in the two-sensor approach, like you might have a fourth state, right? So if I'm robot, and let's say my software makes me veer away from the wall a certain amount, I can always still read like front sensors distance, even if I'm using a two-sensor approach. If I get too far, I can have a fourth state that just says, okay, I just need to turn it. So you can do a combination of the two approaches. The only thing that limits that move all the furniture away from the competition area, the only thing that limits that is once you get, even with the long range, once you get about a meter away from the track, it's obvious that you can't. It'll start generating the distance. Okay, so that being said, we won't like have obstacles that restrict you. It's really based on restriction.
Fair number of sensors.
No, so there's no limit, but it also be reflecting your cost limit. That's what makes that, right? So if you want to take the 3 IR sensors, you can. Because there's no obstacle directly in front of you, there's no huge benefit. At least this is my opinion for having a third sensor. That being said, I mean, you might say to yourself, all right, I just want to fail safe. Next, and then you might have a third sensor. I guess that is fine. But you'll notice if you guys put together your first kind of design, you'll notice that the cost budget is pretty tight. So if you add a third sensor, you're going to have to take away something like the port. So as an example, there's a little 6-volt battery that you guys can purchase to get a little bit more power. You probably will not be able to afford that and a third IR. So that's going to be up to you. Great question. So only thing you will not know until the day of the competition is the direction of the track. All right, so you got to be prepared to modify. Okay, so the easiest thing to do, in my opinion, is just to have 2 different versions of your code. Have a clockwise version, have a counterclockwise version, and then just be able to kind of be ready to roll and just switch the sensor direction. All right, that's, in my opinion, that's the easiest thing to do. That way you don't lose track of what your settings are. You are programmed clockwise and counterclockwise. Day of competition, about an hour before the competition, we will write the track direction on the board. So you will have a little bit of time to just kind of metabolize, okay, this is the direction, and I need to prepare for that. Okay. Other questions? Yes. Right. I haven't looked up And it should be set up today. Other questions?
Is this something where we can like, mess around with the design of it and maybe like turn it back and correct it? We change the design of our car, we
Yeah, so you'll be able to tweak things, add parts or subtract parts at will through the competition. The only thing that will factor in is at the end, we're going to look at what you have. We're going to look at make sure that you're under budget. You can't have something that's like over budget for like 3 rounds, and then at the end for the last round, like take off a bunch of stuff. So, you know, just don't kind of try to trick the system, but you'll be able to tweak things. So you might like have one run that's really a little bit shaky, and you can make adjustments in software, grab a computer, maybe make stuff a little bit more conservative in your settings on your speeds. You can tweak your hardware. Maybe your sensor placement is a little off. You change the angle of that. All that stuff is fair game. You just need to be ready to kind of rock and roll when your number is called on the competitive board. Yes. Yeah, we'll go over it for safety kind of stuff. Really, the bulk of it is you got to kind of get started and you know, prototype first. Once you show us the kind of starting point, let's say you build the robot friendly and you're ready to go with your hardware and that's hardware, then your first design, show us everything in the CNA, you'll toss you a wheel, you'll toss you a battery, so that way we can start that. We have a little bit of buffer there, just to kind of force you guys to think through the hardware. Other questions? We'll do the same thing we did with the project in terms of we hope that you guys stay in the lab. If you have a conflict that is at this point not reconcilable, and we will allow you guys to communicate with us and you guys can do stuff. The easiest thing is to stay for lab. Can we add it? Yeah, we'll just have to do it on case by case. Other questions? All right. Since we have this, let me try to just throw something out there that are factors in performance. One thing that is a factor that we might consider: debris in the lab area. Okay, debris in the lab area. Okay, you will probably want to wipe wheels before competition, just to make sure that you don't have too much slippage, that you don't end up with an issue there. Also, we're giving you guys the track beforehand, so any kind of little quirks with the track, you should be able to test it enough amount of time to have an understanding of the track. All right, so you guys will have the track as it is going to be for competition. Beforehand, you'll be able to see what things impact my robot's performance. But to be honest, it's going to be very similar to the rectangular shape. Like you might do, we've done this before, where we've added like panels here, changed this to a hexagonal shape. But also just to make sure you guys understand or are aware, we've also done this before. We've added panels here and here as an example. In this case, you can have a case where you're going in and it's kind of really kind of sharp change here. The robot is going into like a shallow area. That is significant. You're going to want to take that into account. You're going to want to test enough time. Get a feel for the track, get a feel for the environment. And with any robotics application, you know, all the robot is, the reason why we do it last, all the robot is a data acquisition system that uses sensors in the environment. It uses sensor and sensing and actuation. That's all the robot is. All right. right, and so with that being said, you guys have now seen, especially with the camera lab, that your environment can be very impactful on the performance. So you're going to want to do stuff like clean wheels off, right? You're going to want to do stuff like get familiar with the track. All these things will help you. All right, I want to go back to.
How do we start with this? On an hour, you start running or?
So the way the program is set up, the show program, load up your code, and it doesn't do anything until there's a full button you want to read it. Press button and it'll start your. So the way procedurally, the way it will work is this competitive portion. I'll place my robot on the track. We'll do a countdown, 3, 2, 1. All you can touch is the button, hit button, and both will start at the same time. All right. So we mentioned the chase game. I want to spend a little time talking about this section, competition and the qualifying. All right, so qualifying. You guys saw the schedule where you guys will have reserved time to go to the lab with TAs present to log qualifying time. Just like other kinds of races, you guys are going to get a time trial. That's what qualifying is. And so you place your robot on the track, you say, tell TA, all right, I want to get an official time. TA will start stopwatch, one lap around the arena, and we'll time it. Hit stop and stopwatch. What's going to happen is TA is going to say, do you want to lock this in? If you tell the TA that you want to lock the time in, you can't adjust it after locking it. It's the qualifying time. If you don't like the time, you don't want to lock it in, you can say no, you keep running and running and running until you get a good time. All right, but once you lock it in, it's going to get recorded. All right, and we're going to, you have to qualify before you come to participate in the competitive portion. You'll have a qualifying time, you will not be eligible for the competitive portion. One slight caveat is, well, let me hold that and talk about assessment. So, all robots that qualify will progress to the phase 2, which is the competitive portion. The single elimination tournament, the knockout game. All right, and so we'll go through the knockout game. The knockout game is for extra credit. So, 4 points total for data acquisition, 6. 3 are a memo that you will write, like the other data acquisition. And a memo, 3 points for the memo, 1 point for qualifying. So that's a total of 4. Everything that happens during the competitive portion is extra credit. So that's why I said if you're really just concerned with, I just want to get the 4 points, it's something that is slow and reliable. All right, and you get around the track one time, get an official time for the TAs, turn your memo in for full credit, and qualify. That's 4 points. That's 4 out of 4. That's 4 credit. If you're a competitive person, you say, all right, I'm just going to win this whole thing, all right, and you're going to put a lot of energy into optimizing. Get something that works first, make it faster, make it more reliable. Right, that's going to make you more competitive for the single elimination tournament. All right, so since I'm mentioning the assessment, I want to mention one caveat. What we will do is, let's say that you get something in lab, you're working there, there's no TA. We will allow you to, on your phone or whatever video you have, capture the robot getting around one lap for partial credit. So let's say that you're trying to qualify, nothing is working with the TA present, and this happens with teams, right? They have something that works. Well, hey, Dr. James, it was working. So the first, if you say that to me, the first thing I'm going to say is, okay, show me the video of it working. And if you can verify with the TAs and show the TAs and show me a video of it working, we'll give you half point on the qualifying credit. It'll give you half credit on qualifying. If you only have a video and you don't qualify officially, you will still not be able to participate in competitive. Competitive is only for teams that have an official qualifying time. But if you are not able to qualify and you have the video, you can get that half point partial credit for qualifying. All right, instructions here say you have the shell program. There's one campus already. You also have a couple of videos from YouTube here. These really are more so given for perspective. These will not be nearly as helpful as the videos I posted on campus. These give you a perspective on IR Center, give you perspective on your background, how they work, give you perspective on how to connect them. Useful information, but if you watch our videos on campus, they will do a good job walking you through how to use the video at IR Center. You also you know the parts that are eligible that we have in the lab. Those are on your call sheet. So we'll pull up the call sheet in a second. But if you have any doubts or questions about the parts, all you have to do is look up the part number on the Visco Tetris Prime. So here's Tetris Prime. Let's say that I want to. I'm at home and I just want to kind of get a better understanding of one of the connectors. You can go to the website, you can look it up, you can see its dimensions, you can learn more about it. All that information can be accessed. All right, and then we mentioned this also already, but when you guys asked about getting started, TA is, we're not going to toss you guys a Rio as a team until you've shown us a little bit of progress with the hardware. So as this says draft for a reason, as we stated, you can continue to update your robot all the way through competition. But we do need to see something that is reasonable. So we need to see, like in most of the robot designs, you're going to have like really two approaches that people have used. All right, differentially steered, which means that you have servo and a wheel on each side, and depending on how fast each side spins, it's the behavior that you're going to do. Differentially steered. The other approach that we see is just like a traditional car, and so we have servos that are called continuous rotation servos that will spin like a DC motor. All right, and we also have standard servos. And if you guys work with servos, you know that a standard servo just moves to a particular position. You got a standard servo that controls like the steering and a continuous rotation on the back that's drive. We've also seen that approach. So standard servo and continuous. Now I'll say a little more about that today as well. Standard servo versus continuous rotation. We'll mention that today. To solidify that idea. All right, but you're going to have to show, so when the TA looks at your kind of starting point, it probably should reflect, it should be kind of a robot hardware that will work, right? So you should see like differential steer setup, you see car kind of steering setup, something that makes sense. Once you're able to show that, you also need to show the TA that you have logged your parts into the Excel spreadsheet. That does the cost analysis. So we need to see something that is under cost and reasonable. Okay, once you're able to show that, TA will toss you my Rio and battery for you guys. All right. So in order to have something that works, right, you have to have a Rio. We're going to also toss you guys battery charger for your MyRio is going to need to be battery powered. So it's not like the MyDAC. So if you guys remember MyDAC, you just plug MyDAC in via USB and it's ready to go. With the MyRio, you need to provide about 10 volts of power. All right, so everybody have these little 9.6 volt batteries in the lab. They'll toss you one of those. Once you get your Rio, that will make your Rio wireless without being tethered to a computer. So that 10 volt battery will power Rio. In addition, in order to drive the servos, so my Rio, standard my Rio, will not be able to drive the servos like we need. So we need to add a little bit of additional hardware. There's a motor control board that will drive the motors on the Rio. All right, so you have to use a motor control board for that. Each motor control board can use 2 servos. So Rio actually can support 2 motor control boards at once. Right? It can control up to, really, honestly, if you go actually into the I/O, you can control up to 6 servos with Rio. The motor control board is only designed to access 2 out of 3 on a connector. The motor control board, you need to have at least 1, you need to have at least 2 servos. All right? Now, the question of can I use more than 2 servos? So technically speaking, yeah, you could. All right, what would that look like? You have to purchase 2 motor control boards in order to access more than 2 servos. All right. This is also an important point to realize on our cost sheet. All connectors are at no cost. All connectors. So when we say connectors, we're talking about nuts, bolts, zip ties, really no glue, guys. All right, because one of our stipulations is nothing should leave behind a residue. So don't have glue to call this together, okay? Because no residue should be left behind. Don't use elders glue, right? Don't leave residue. Take the spare game, okay? Anything that's a fastener or a connector, that does not impact your cost. Zip ties are my best friend, so I'll suggest you guys maybe run to Walmart and get a little pack of zip ties or something, and you can just do a lot with some zip ties. All right, those things are at no cost. This talks about battery holder. We've actually replaced this battery. So we have battery holders where you can provide your own AA batteries if you like. But most of you guys, for this power with the Myra 10 volt battery. So we have to charge the batteries now. You just use the rechargeable power of the I want you guys to jot a quick note about this next thing because on the cost sheet it says 6 volt battery. You can use a 6 volt battery to power the motor control board. Right? If you use the 6 volt battery to power the motor control board, you will get a little bit of additional performance. You'll get a little bit of additional performance. In fact, what the TAs will likely do when you get your Rio, they likely will give you access to a 6 volt battery, even if it's not in your plan, just so that you can get a feel for what the performance is. But the way the motor control board is in the Rio is you can also power the motor control board directly from Rio. You can wire up these 6 volts, you can wire Rio's 5 volts ground to the motor control board. It will work, but you just won't get the same performance. So why would you not use the battery? Well, let's say that your cost budget is capped out. You might not be able to afford the 6 volt battery. These are all things that go balance when you build your robot. Let's say you don't want to even deal with the battery at all. You don't want to have to worry about it. You don't want to charge it. You don't want to keep track of it. That's fine. You can power the motor control board directly. You don't have to worry about it at all. We take some precautions with wiring up battery or any type of power to this hardware. So I also do need to say this because it's like with the op-amp, okay? We don't want to let the smoke out. We don't want to let the smoke out, okay? These robots, they have smoke in them. If you touch black and red together, you're going to let the smoke out. I've seen probably about 4 years ago, they just kind of standing there. Like, don't you guys smell that smoke? And they're a robot, and they had touched black and red and just started melting components. It was a complete mess. And the battery will melt. It will be a complete disaster. Please be careful when you're connecting up power. So we have connectors that we want you guys to use to try to help you guys not make mistakes like that. But please be careful with our hardware. All right. So you guys understand that there's a 10-volt battery that will be needed to power the Rio, and then there's an additional optional 6-volt battery to be used to give you a little bit of an advantage on power for control. All right. Okay, this gives you kind of an overview of what we would kind of expect you guys to do to get started, right? So one of the first things you're going to do is download the shell program. Let me say a word as well about the sub-VI. So this is the same sub-VI that you guys use. We use to calibrate the IR sensors. The calibration that we've done on those IR sensors is not a perfect calibration. Right, it's not perfect. So if you're one of those people, you say, hey, I want to make sure that my IR sensor gives me a little bit better conversion of the distance, feel free to do your own, use your own calibration. And you can open up our sub-VI, you can use your calibration that you had earlier in the semester, you can recalibrate, you can adjust, feel free to do that. But most of you guys are going to use our sub-VI that we provide for you guys. All right, so another objective that we have, we're not going to get to this today, guys, but one other objective we have is MyRio is programmable through the LabVIEW project structure. LabVIEW project. And we're going to learn, we'll probably get to that on Monday. LabVIEW project structure is just like other programming languages. You guys have probably used other languages where you really need to organize your dependencies. Right? You need to identify what libraries you want to use. And you need to identify all these different things so I can access all the dependencies and the program compliance. The beauty of LabVIEW is it does almost all of that stuff for you in terms of dependencies, in terms of making sure that program has what it needs, make sure you find all your functions, all your sub-VIs. It's almost all done for you. The only thing that you need to do, though, is you need to set up a LabVIEW project. So if you think about it, as soon as you plug in your Rio, and you plug in your Rio to a desktop computer, there are now two computers that play. There's your desktop, and then there's the target of the Rio. So the project allows you to specify, where do I want to run this code? Do I want to run this on board the Rio, or do I want to run it on board my computer? Project structure also says these are the dependencies. Once you have a top-level VI in project structure in the project, it will add all the dependencies for you. But we need the project to organize all that stuff. Okay, so the LabVIEW MyRio project is key. You cannot just open up the program from the shell or from Canvas and hit run, and it's not going to work. The programs that we provide for you guys require your understanding and setting up the MyRio project. So we won't get into the kind of meat of that on Monday. All right, but the project stuff is not difficult. In fact, LabVIEW does almost everything kind of automatically for you. You just need to kind of expose you guys to what that is. All right, so you're going to create a MyRio project. You're going to add your shell program. to the MyRio project. All right. Another quick note that you guys can make about the Rio. Rio can operate in wired mode and also as an access point. Okay. If you're in wired mode, you're just going to connect it up through USB to a computer. You're going to program it just by hitting go on a computer with it wired directly. If you configure the Rio as an access point, so anything that's an access point, guys, is going to broadcast itself. You guys might have printers, as an example, that operate as an access point, or whatever the case may be. You might be able to configure your phone as a access point. So once you configure Rio as an access point, it'll pop up. It'll say, like, if you look for wireless options, it will pop up as like Rio 1, Rio 3, or whatever the case may be. And then you can actually connect up your computer in the lab to the Rio. So what are the benefits of being wireless? If you're wireless and you're trying to troubleshoot a robot, it can be running around the track. And if you have controls in your shell program, your main, you're not using constants, you have controls. You can actually change the value, you can change the threshold, you can change the distance comparison in real time. While you watch the robot kind of try to go around the track, you can change the speeds. If there are controls, just like you guys are familiar with LabVIEW at this point, if you have controls, you're able to change those things on the fly. So that might be a benefit, depending on. But honestly, guys, you don't need it to be wireless at all. You can just program it. So what would it look like if all I wanted to rely on was hardwired? I would just connect up my robot to the computer. I hit run on my LabVIEW program. It will compile the code on my robot. I then have to disconnect the robot, place it, run, see what the effect is, and I pick it up, and I re-separate back to the. That also is perfectly okay. All right. Okay, so step says you're going to want to insert your VI, sub-VIs into your logics. You're going to create state machining with your logic in LabVIEW. All right, so once you're able to get all the parts that you need, you have the shell program, you're going to insert in the shell program the part where you're grabbing information from sensors. That's 4. You're going to insert into the shell program the part where you're using the sensor information to drive some behavior from the robot. That's what a state machine is. All the state machine does is sensor information that's an input, and then outputs what it wants motors to do. It drives what state am I going to operate in as a robot. All right, we're going to talk a little bit about this. It's going to sense and follow the track. We already touched on this assessment here. So as we said, 1 point for qualifying, extra credit for the competitive portion. One thing that I want to highlight about the competitive portion, that we made this mistake a couple of years ago. We had these 2 robots that were the exact same speed. Like we started both of them, and we watched them for like 10 minutes, and they just followed each other around for about 10 minutes. And after 10 minutes, we're like, we can't just continue just sitting here and hoping for something to happen. So we moved the robots to a very small track. When I say small, it was like foot by 2 feet. Starting on the small, they still spin around and going at the exact same. So we didn't have any stipulation that allowed us to award a winner when the robots were the exact same speed. So there are 2 things. After 3 minutes, we're going to stop the competition. Just time for 3 minutes. After 3 minutes, whoever is closer, and it is very obvious, you'll be able to say that robot is closer, that's the winner. If it's not obvious, or if it's exactly the same, what are we going to do? We're going to go to the cost budget. Lighter robot is going to win if it's a tie after 3 minutes. So we said there's a slight benefit to going below the cost budget, that's the benefit. So if you have a tie and you're lower in cost, you're going to be the robot. Also want to point out another kind of stipulation here. For the competitive portion, we have rewarded, well, let's say we start 2 robots, all right, and both of them immediately crash into the system. Then we'll reset one time. It goes, and if they both crash again without doing a half lap, they'll both be disqualified. They can't just kind of have a robot that moves like 2 feet and another one moves 1 and say that one won. That doesn't make a lot of sense, right? So you have to complete a half lap in order to be eligible to advance. If both robots get disqualified, the benefit will be on the other team that's waiting for the winner. So that will be an immediate buy to the other team. All right. Okay. All right. So here we have extra credit levels. I'm not going to set the extra credit levels today. Okay. What I'm going to do is I'm going to look at kind of let's say that you guys just really abuse the lab. And the extra credit levels, we'll set them lower than what we would. Guys are good stewards of the lab, you clean up after yourself, you put stuff away, and we don't have an issue with anything like that. All right, so I'm not going to set the extra, I will say conservatively, the winning team will get probably on the order of 1.5, 2 points extra credit on the final grade. That's conservative. We could do more than that. Okay, we'll have a winner for the class determined during the final exam period. And we might do more than 2 points. It all depends on how things go. All right, so this is emphasized here. Clean up during this whole process. We expect you guys to be good stewards of the lab. We also expect you guys to have competition to clean up after yourself. If you get eliminated, we're going to expect that you disassemble and all that good stuff with the TA. Also, just so you guys are prepared for this, a little bit of unnecessary per se. But they have the competitive portion. We will use the CAD lab and we will use the Lab 2000, ESP 2000. Because you pre-qualify, you'll know who your matchup is before the day of the tournament. You'll see the whole bracket. We'll send it out to you guys before the final exam period. So those of you guys that are not going to be up first, we're going to probably place you guys in the CAD lab. CAD lab, y'all can load up your code, you can try out different things. And we'll probably take the losers from the competitive portion, they'll come down to CAD lab and disassemble. And then we'll rotate other people into the lab. So procedurally, that's how it does. Otherwise, we try to fit all you guys into one room. It's going to get hectic quickly. So we'll have a strategy for making sure that you'll know like when you're expected to be in the ESC 2000. So we'll announce that beforehand. All right, this last little portion here, guys, is detailing the memo. So we've outlined what you guys can give us. And so just follow the directions, as always, guys. Follow these directions, include this information. It's going to be full credit. And so, but I do need to make sure I mention this. You can't like not do the robotics project at all, and then show up. And you can't not have anything and then turn the memo in. All right. You have to show up to the final exam period. You need to have something that is reasonable in order to be eligible for the. You don't have to qualify, so you don't have to have something that gets around one time, say. But you also can't have nothing. Okay, you can't just. We had a student that tried that one semester. He just kind of said, "Okay, I'm not going to do anything," and turn in a memo. That's not going to be acceptable. All right, so you're going to need to show up to the final exam period, even if you're not qualified. You need to stay the entire time. Because it's not fair to your classmates when you just find on the project and just not show up. So going to require all you guys to show up to the final exam in order to turn in the this last statement is about the structured videos. We already mentioned that. Any questions, guys, about the rules? We have to clarify. All right. Let me show you guys the cost budget sheet. All right. So if I'm you, I get started on this. I've started pulling parts and immediately covered the cost budget. So you have to go back and forth. And it's this link here, Robotics Competition Parts List 2019. All right. So it tells you on the top here, your budget is $375. This says you must buy 2 continuous rotation servos. I'm actually going to allow. I do have standard servos. So this is just say you must buy 2 servos. You must buy 2 servos. So I'm not going to force you guys to use a little bit more room on your budget. I'm forcing you to buy 2 continuous rotations. You can buy 1 continuous rotation and 1 standard servo. You can't do it with 2 standard servos. Again, that would not work. And you need at least 1 continuous rotation. You have to have a motor control board. You have to purchase a wiring. And in addition, goes without saying, you need at least 1 sensors, you need an IR sensor of some type. And so we mentioned bearings and fasteners for cost. We mentioned you can look it up on the website. And we will check for compliance with the cost budget. So all you have to do is just go through and just plug in what you have, your robots components, sum it up for you. The required parts are already in, so you need a reel, you need a motor control board. Here is log is 2 continuous rotations, but you can do 1 and 1 here if you want, 1 continuous rotation, 1 standard. And the cost is here. So as you can see, kind of start off at $261. All right, so everything else that you buy, so the sums of that, the vectors, and the beams are the main components. If you find an item in the lab that's from Tetrix Prime, and it's not on the cost sheet, I will add it. And I'll assign the cost value. So as an example, we have Omni wheels in the library. Let's say you find an Omni wheel and you want to use it. That's from Tetrix Prime. So I will add that. And in fact, in this case, it's already added. It's called a small Omni wheel, large Omni wheel. If you want to switch, just go to the website and look it up. The last thing I want to mention to you guys, I want to just mention is called continuous rotation for standard. Servos, honestly, are all they are a really extremely motor that's very high speed. A compound gear train. So, like, if you open up a servo, one of the first things you'll see is a compound gear train. Compound gear train, high speed, low cost motor, and then some smarts for doing some motor control. Because a servo is a control system. That's one thing in the dots. We talked a little bit about controls. But a servo in a standard kind of capacity, it has an arm that will go to the position based on what you set up. You tell it to be extreme left, it's going to be here. You tell it to be extreme right, it's going to converge to here. So it converges to a set point. That's what a servo does. Converges to a set point. And so if you're using continuous rotation servo, you use pulse width modulation. We'll talk about that next time. You tell it, yeah, I want to steer this way. I want to steer this way. You're going to be able to move to the position. Standard servo. And all a continuous rotation servo is, guys, a continuous rotation servo is just a hat. It's a hat. All a continuous rotation servo is, it makes constant the set point, all right, to be in one position. And it just breaks the feedback. So with the continuous rotation servo, it will try, if you try to kind of tell it to move away from the set point, it's going to try to converge, but it will never know that it converged. So it will continue to spin. That's what a continuous rotation servo. You can actually converge any standard servo to continuous rotation. All you have to do is break the feedback. Remove the understanding that the servo converges. If it's trying to converge one direction, it's going to spin clockwise. Trying to converge the other direction, it's going to spin counterclockwise. All right, so we're going to use continuous rotation servos. Most of you guys will use differentially steered, but others of you guys can use the continuous rotation, drive forward, backwards, whatever you want to call it, use a pulse width modulation. We'll talk about that in a lot of detail next time. That's all I have for you guys. Okay.